All right, welcome to the course Design of Machine Elements and Systems in ABE. This is lecture number 3, and the topic for this lecture is on velocity analysis until the next, okay? Previously, the topic was on position analysis, and this is the way forward is velocity analysis, so that afterwards will be acceleration analysis. Now, this is still part of the kinematics discussion or main topic, okay, before proceeding to actual machine design. Now, the the topic on velocity analysis hosts a list of subtopics as shown, okay, and again, the study of kinematics is founded on the uh, topics of statics and dynamics. And thus, it is a prerogative that a learner of this course should have already or already knows what velocity is. Okay, and just to start out the discussion, okay, we define velocity, okay, and it's the rate of change of the position of an object with respect to a reference frame, okay, and as a function of time, okay, depicted by the equation v equals delta x over delta t, and with a specified direction. Okay. Now, there are four main topics to be discussed in velocity analysis. We have graphical velocity analysis, instant centers of velocity, or what is otherwise referred to as instantaneous axis of velocity, or IAOV. And the centroids, okay, a more advanced topic related to the IAOV, or the instant centers of velocity. And the next would be velocity of slips. In this lecture, the discussion will be on graphical velocity analysis alone, okay? Now, the instant centers of velocity will be discussed, okay, with the centroids and the velocity of slips in the next as a whole topic group of topic. Okay, so let's discuss, okay, an example, and this topic, or this main topic of velocity analysis is very hands-on. It involves, okay, solutions. Now, the solution of velocity analysis is based on dynamics. It actually involves analytical methods, but that should have been a given, okay, before this course on machine design. So we proceed immediately with the graphical velocity analysis, and this would be no better than an example, okay? And we have here a slider crank mechanism, okay? Slider crank, so you have cranks, okay, and a slider, okay? So this is the slider, okay, and you have your the crank, okay. But I think I made some mistake from my end, okay. So let's okay, so this is the slider, this is the slider, okay, and this is the crank, okay. Okay, so sorry, this is the actual crank mechanism, okay. Right, so what happens is, okay, you have here the given, okay, the given crank, okay, rotating or move, no, the velocity of that, so the angular velocity is not provided, but at that instant, okay, at this instant, okay, the velocity of p, which is a part of the crank okay, 01B is 20 centimeters per second. Now, what is being asked, okay, here is, okay, find the velocity of the slider at point C, okay, if the crank rotates counterclockwise as shown, okay. So you already have the velocity of B, okay. So we have, okay, velocity of B known. We also know, okay, probably, oh yeah, you can easily compute for the uh, angular velocity of this crank 01B with respect to the pin at 01, 0.01, okay, 0.01, okay. Now, what we do not know is the velocity of this crank or this arm, okay, this link BC, okay, and this is the slider. Although we know, okay, that this slider is advancing to this position because we have this crank rotating this way. We also know, okay, that at this current position, okay, B is, or the link BC, okay, would have a velocity, okay, directed along this position, okay. We do not know then its magnitude. So we, okay, we write down the given, okay, VB is equal to 20 centimeters per second. So known in magnitude and direction. VC, okay, is known, okay, sorry, this is known in direction and VC with respect to B, okay, is also known in direction. Now, where does the graphical analysis or solution come in? Where does it come in? Okay. We know, okay, from the relative velocity concept, okay, from dynamics, we know that VCB is equal to what? It's V of C minus V sub B. And this is a vectorial addition, so we denote this as that, okay. How do we do that now? So if there's a vectorial addition, okay, we proceed now to the graphical solution, which requires us the velocity polygon. So we construct the velocity polygon using the known parameters. Okay, so let's proceed with this solution. Over in this representation of the diagram of that given case ladder crank mechanism. Now we have the same, okay, this is a simplified diagram just to show the moving or the significant parts, okay, from the slider, okay, from the slider, okay, from the slider over here, okay, something like that, and we have this crank rotating about this point O sub 1. Now, okay, we know, okay, that the velocity of okay, the velocity of VB, okay, this is point B, is 20, okay, about this one, it should be 90 degrees, okay, given because it's it's actually the normal, I know, the tangential velocity of this crank with respect to 0, 1. All right, so we create the a line, okay, that is, well, it could be in the same magnitude as this one, okay, Let's see, and let's try to do that. Okay, let's create a line that is along this line, and we rotate that by 90 degrees. Sorry, base point 90 degrees. Right, so that is the direction of that V sub B, and we just have to move. Okay, move. Okay, copy this. No, I just want to offset this one. Okay, just want to offset this line to create the magnitude, okay, of 20. Okay, offset. Okay, so this is going to be the what? The magnitude of this V sub B. Okay. Let's change the color so that it's, sorry. Let's change the color to right. So delete this one and write us this one. So we have now, this is now V sub B. Okay. At 20 centimeters per second. Let's see if it's consistent. No. Should be, because anyway, let's just check that later. Now we know the magnitude, no, the directions of the other two velocities. Okay, we know that. Okay, we know that V sub C, okay, with respect to B is equal to velocity of C minus B, velocity of B. So vectorially, okay, we have VC along this line. Okay, so it's going to be along this line. Okay, we are going to create the velocity polygon. So that's why we want to know the because we want to know the velocity of C. Okay. Now, how about the velocity of C with respect to B? Okay, it should be again perpendicular to that link. Okay, this is point B, this is point C at that given instant. Okay, so we know now that this is going to be the direction. Okay, the direction of V of C with respect to B, or the velocity of C relative to B. 90 degrees. Okay, so we just move. Okay, we move this line, or recreate a line that is going to be 90 degrees with respect to that link. Okay, so we rotate this one. Rotate this one with respect to C, 90 degrees. All right. So we now, what we do now is we connect this line. Okay. We move this line from here to, oh, sorry. We have to move. We move this one over here so that we get now the vector, the velocity polygon. So velocity polygon, where we have V sub B here, V sub C with respect to B here, and we have the what we intend to find, V sub C over here. Now to get the value, we just simply we simply get the value, or we get or we measure, okay, because we know, okay, so we know that this is drawn to the actual length of the magnitude. Okay, so this is going to be V sub c. Okay, and we just move over or look up. Okay, so the velocity of V sub b is what? It's going to be V sub b. Okay, V sub c with respect to b is 7.9 centimeters squared per second. Sorry, and we have, okay, we have our V sub c now, but we have our V sub c equal to, okay, 22.7. Okay, is it 22.7? Or is it, probably it's correct? Yeah, I think it's correct. 7.9 and 7.22.7. Okay. Now, this is the graphical solution. Okay, this should check with the analytical solution of the same problem, and that's what we're going to do in the next topic on instantaneous centers of velocity. The solution will be, okay, via or using the instant center of velocity. So I'll see you next lecture.